All right, we're going to start this chapter by going and reviewing and looking at complex number systems. You should have had some introductions to the complex number system in the ET111 course and possibly in your math courses. So we're going to look at complex numbers. Again, I recommend that you look at the ET111 Math for Electronics course. I've got a couple of good videos in there using that text for explanations that will help to reinforce what we're doing with our complex numbers. So complex numbers allow mathematical operations with phasor quantities. We're going to be using phasor quantities more and more as we progress through the next few chapters. They're useful in the analysis of AC circuits. You didn't need them in DC, but you certainly do need them in AC. With the complex number system, you can add, subtract, multiply, and divide quantities that have both magnitude and angle. And this is important when we try to translate what's going on in a sine wave representation versus a phasor or a complex value representation in AC circuits. AC circuits are full of using the analysis of complex numbers, using complex numbers, but you also need to use your calculator. Most scientific calculators can perform operations with complex numbers. Refer to your user's manual for exact procedures. And again, we recommend for this course that you get and use a Casio FX115ES Plus, but if you have something else, even your phone with a calculator on it will work. So you're probably used to the Cartesian system, the Cartesian and rectangular system, which is represented here, positive and negative numbers. We learned in X space the number line from the origin out positive to the origin negative. We have this positive and negative relationship then when we combine it with another axis, the y-axis or the two-dimensional axis, where we have the positive going up, the negative going down. So we're going to take what we learned about Cartesian and rectangular coordinate systems, the two-dimensional system, and we're going to apply it to the complex plane. So positive numbers are represented by points to the right of the origin on the horizontal axis of the graph. Negative numbers are represented by points to the left of the origin. Positive numbers are represented by points vertically above the origin. Negative numbers represented by points below the origin. So we're going to translate this rectangular Cartesian system over to something called the complex plane. So in the complex plane, we have a real axis, which is your x-axis, and an imaginary axis, which is your plus and minus j-axis. To distinguish then between the values on the horizontal axis and the values on the vertical axis, we call this a complex plane. In the complex plane, the horizontal axis is called the real axis. The vertical axis is called the imaginary axis. In electrical circuit work, we use a plus and minus prefix to designate the numbers that lie on the vertical imaginary axis in order to distinguish them from numbers lying on the horizontal plane, the real axis. This prefix is known as the J operator. In mathematics, you probably learned to use an I operator, but we use a J instead because in electric circuits, the I has already been defined for instantaneous current. So the next thing we need to do then is look at the angular relationship, the angular position then on that complex plane. So now you can see here we've been introduced in 4 quadrants an angular relationship from 0 to 90 to 180 to 270 and back to 0 or 360. Angular positions are represented on the complex plane as shown in the figure. The positive real axis represents 0 degrees. We proceed counterclockwise. We can go clockwise, but that's a negative value. So we're going to go counterclockwise positive. The xj the plus J axis represents 90 degrees. The negative and real axis then represented by 180 degrees. The negative J axis 100 or 270 degrees, and then back to 0 or 360, making one full rotation from quadrant to quadrant around the axis. So notice that the plane then is divided into those four quadrants. So representing a point then on a complex plane, right now we're not going to make the line, which really becomes the hypotenuse of our triangle, or our vector or phasor. We're just going to look at the points here. A point located on a complex plane is classified as real and imaginary, or combinations of both. A point located 4 units from the origin to the positive real axis is the positive real number, plus 4. A point 2 units from the origin on the negative real axis is a negative real number, minus 2. A point on the plus J axis 6 units from the origin then is a positive imaginary number, plus J6. And then finally, a point 5 units along the minus J axis is the negative imaginary number, minus J5. So you can see we've put all these points here as we've mapped them out in the complex plane. When a point lies not on any axis but somewhere in one of the four quadrants then out in two space, it's a complex number and is defined by its coordinates. The point located in the first quadrant has a real value of plus 4 and plus J6. In the second quadrant, minus 3 and plus J2. In the third quadrant, minus 3, minus J5. And finally in the fourth quadrant, plus 6, minus J4. Taking a look at an example here, we've got a two-part example, A and B. A refers to the diagram to the right here. B is the diagram below. So what we're going to look at here is locating these points. Notice they're in pairs. 7, J5, 5 minus J2, minus 3.5, J1, and minus 5.5, minus J6.5. So if we take a look at each of those, you can see 5, J5, minus 3.5, J1, minus 5.5, minus J6.5, and then 5 minus J2 relates to each of these pairs. If we take a look at part B here, we have several points that we've plotted. They want you to take a look at this and determine point A, where is it located? Well, point A is 2 on the x-axis, J6 on the positive J-axis. B down here is 11, J1, so you can see we're out at 11, we're up J1 units, and so on. So you've got A, B, C, D, E, F, G, A, and H, each one of them plotted on the graph here below. So the next thing we need to look at is, what does that J mean? It actually is a value, and so we need to determine what the value of J is. And when we come back, we'll take a look at that in the next video.